All right, today we'll be looking at section 4.6. So we looked at the graphs of the sine and the cosine functions. Today we're going to look at the graphs of the other trig functions, and we're going to start with the tangent function. So this is first asking, is tangent an even or an odd function? And we learned that tangent is an odd function. And what that tells us about the symmetry of the graph is that tells us that it's symmetric about the origin. Okay. We also know from the quotient properties that tangent of x equals sine of x over the cosine of x. So what that means is that because we're dividing by cosine of x, that cannot be 0. Tangent of x then is going to be undefined when the cosine of x equals 0. When is the cosine of x equal to 0? Well, that is going to be along the y-axis. Okay, and so notice at plus or minus pi over 2, it's going to be undefined. So if we thought about that point at that angle at negative pi over 2 to pi over 2, these are the values between here and here are going to be the values that we could use to try to find one of those cycles. And some convenient values for us to use are going to be at 0, but also if we think about the value of tangent at plus or minus pi fourths, that's a nice value of 1 also. Okay, so if I'm thinking about graphing, what we've done in the past is we've made a little table, and for tangent we know, like I'll just kind of put this in parentheses, that if we had negative pi halves, that would be undefined. But if we had negative pi fourths, we could evaluate that at negative 1. 0 would be 0. The tangent of positive pi fourths would be 1. And then again, I'll just put this in parentheses. At positive pi halves, it would be undefined. And again, I'm not putting that, I'm putting that in parentheses because that will kind of help us determine that'll help us determine what the asymptotes are, which we'll talk to you guys about in a second. So notice because it's undefined, that means that if I label my axis, I'm going to go every pi fourths this time, since in these critical values for tangent, the ones for pi fourths are pretty handy. Okay. So what that means is that we are going to have some undefined values. And when a function is undefined, what we find is that there is an asymptote. And so that means that at negative pi over 2 and at pi over 2, there will be asymptotes. And then if you plot the actual points of this graph, oh, let me make a scale over here too. Let's make this 1 and this negative 1. If we plot negative pi over fourths, negative 1, 0, 0, and then pi fourths 1, notice it looks like a straight line, but actually what's happening is that the shape of the function looks something like this. So it'll approach the asymptote on each of those sides, right? But that's the shape of our tangent function. And then what happens is that this is what repeats over and over and over again. So what that tells us about the tangent function is that tells us that the period of the tangent function is not 2 pi. The period of the tangent function is just pi. The domain of the tangent function in general is that x cannot equal anything that we have on the asymptotes. And so notice that the asymptotes occur every pi units. So x cannot equal n times pi. But notice that the first asymptote is at pi over 2. So again, this just says that you start at pi over 2, and then every pi units, there would be an asymptote. Notice though that the range this time we're not bound by the range at all. Our range is going to be all real numbers. And you have a vertical asymptote basically every time. So again, you could think about starting at that pi over 2. And then we have a vertical asymptote every pi units. So that would continue. So there would be another asymptote at 3 pi halves, another asymptote at negative 3 pi halves, etc. So what would happen is that the pattern would repeat. So notice at 3 pi fourths, we would be at negative 1. At pi, we would be at 0. And then we would continue this way. So it would keep going this way. And if we work this pattern backwards, again, notice that after the asymptote, as we go left at negative 3 pi fourths, it would be positive 1. At pi, it would be negative 1. Or sorry, pi would be 0. And then again, we would just keep approaching that way. All right. So this graph does keep repeating. It's not as pretty as that sine wave, is it? But it does keep going. So here's how we're going to sketch the transformations. The first thing we're going to do is we're going to find our period, but this time our period is not 2 pi over b. Notice that the period of the tangent function is pi over b. And if we look at our scale, notice that this time we're not going by pi halves. Notice our scale is going to be going by pi fourths. And so when we determine the scale of a function that has transformations, we can use pi over 4 over b. So we're going to find the period and the scale. We then can find the vertical asymptotes by setting b times x minus c, which is essentially what you're taking the tangent of. We're going to find the vertical asymptotes by setting what you're taking the tangent of equal to negative pi over 2 and pi over 2, where we kind of found the original asymptotes. The x-intercept will be the middle. We'll complete the RST table using the 3 points, not the undefined values. And then what you'll notice is that when your A is positive, it's going to go up from left to right. And when it's negative, we'll see that it'll go down from left to right. So let's just jump into this example. This is asking us to graph f of x equals negative 2 times the tangent of 2x. Okay, so to find our period, make sure this is in view. So to find our period, what we want to do is we want to take pi over b. Our b value is 2, so I'm going to take pi over 2. There's nothing to simplify. Our period is going to be pi over 2. Our scale is going to be pi over 4 over 2. And so pi over 4 over 2 will give us a scale of pi eighths. So what that tells me is that on the graph, I'm going to make my x-axis go by pi eighths. Okay. So we'll label a couple of those. And it also would be a good idea to determine where our vertical asymptotes are going to be. So we can start by setting our vertical asymptote. We can set what we're taking the tangent, which is 2x. We can set that equal to negative pi over 2. And we can set it equal to positive pi over 2. Notice we're taking the tangent of 2x. So we're going to set that equal to negative pi over 2 and pi over 2. And notice that when we solve, we have x equals negative pi over 4 and x equals pi over 4. And I didn't mark it, but this would be negative pi over 4 and this would be pi over 4. And because our period is 2, notice that our asymptote is going to start at pi fourths. And we're going to have another asymptote every pi over 2 units. So then our next asymptote would be over here. If we look, this is where 3 pi fourths would be. So our next asymptote would be over here at 3 pi fourths. if we continued, this would be negative 3 pi fourths over here. Notice that there'd be another asymptote over here at negative 3 pi fourths. But notice between there, and I didn't label this negative pi fourths, but between each asymptote, notice is that period of pi over 2, okay? But these are where our vertical asymptotes are. As far as the x-intercepts go, we'll look at that in a second. You can see that they're going to be right between the points. I mean, I guess we could plot those if we want right now. So it's going to be right between the asymptotes. Visually in this problem, it's pretty easy to do. Notice that we're actually starting at, we do have a point at 0, 0. And notice that again, because of the period, we have an x-intercept every period, one every period. And so we have, our period is pi over 2n. And then since we started at 0, we wouldn't have to add anything to that x coordinate, but we would have x-intercepts at every pi over 2 units. So let's start talking about the transformations of the parent function. So what we want to do in this case for the reflection is we see that this value is negative here, which means that there's a reflection in the x-axis, which means that my y-coordinate becomes negative. And then I also see that I have a 2 as the coefficient of x. And so that means that I'm going to have a vertical shrink, a horizontal shrink of 1/2. The 2 that's here tells me that I will have a vertical stretch of 2. Notice that there are no transformations. So our parent function for tangent, we're going to use the values that we had up top. So for tangent x, our values are going to be negative pi fourths, negative 1, 0, 0, and pi fourths 1. Okay. Then we're going to do these transformations. Keep the x the same, but change the value of y. Okay. Then we will cut the x value in half and then double the y. Cut the x value in half and double the y. And the nice thing about tangent is that there are only 3 points to plot, right? All right. And so then what we can do is actually plot these points. So we have negative pi eighths, 2. Oh, I need a scale over here too. I just like to wait until I know like what like the values that I'm plotting are before I do that. So I'll go negative pi eighths 2, 0, 0, and then pi eighths negative 2. So notice this one is going down from left to right, which makes sense based on what we were told here. And again, you're just going to repeat that pattern, all right? So, and that's why you go the scale, all right? So if from the asymptote going right, we went from negative 2 to 0, we went from positive 2 to 0 to negative 2. We start at the asymptote, and using the scale, we're going to go from positive 2 to 0 to negative 2. Again, if I start over here at the left from the asymptote using the scale, positive 2, 0, negative 2. And then you would just continue to make that same shape. Sorry, my dot cam is in the way of this one. It looks like a straight line, but it has that kind of curved shape. But notice that it is stretched vertically, you can tell, because of that A value, okay? And notice that there is no amplitude, no min, and no max with the tangent functions because the range is all real numbers, okay? So that's how we would graph our tangent functions. The cotangent function you'll see is going to be very similar to that. Remember that if we have the cotangent, that's going to be cosine over sine. And so that means that cotangent is going to be undefined when sine of x equals 0. So when is sine of x equal to 0? Sine of x is equal to 0 along the x-axis. So at 0 and pi. And so when we think about these values for the cotangent, again, because cotangent is the reciprocal of tangent, why not still go by pi fourths, since those would be pretty easy values to plot as we saw in the other question. Okay, and if we were to make a table for the values, we would start at, like, again, we don't include 0 because that's going to be undefined, but we could use pi fourths, and we know pi fourths tangent is 1, so the reciprocal is 1. At pi halves, the cotangent is 0. At 3 pi fourths, it's -1. And then again at pi, it would be undefined. I shouldn't put a comma there. So at pi, it would be undefined as well. So once again, along the axis, I'm going to make my scale by pi fourths. Because those are places where the points will be easily plotted. So I don't forget, I'm going to make my scale on the y now too. And again, anytime we have something that's undefined, there's going to be an asymptote there. So there's going to be an asymptote at x equals 0. There's going to be an asymptote at x equals pi. And guess what? There's going to be an asymptote every pi unit. So there's going to be another asymptote at 2 pi, another asymptote at 3 pi. Working to the left, there's going to be an asymptote at -pi, an asymptote at -2 pi, etc. Okay? So what we notice here is that our period is going to be pi. Our domain, notice, is a little easier to state this time because one of the asymptotes was at x equals 0. But notice it's going to be every pi units, and so that means that x cannot be equal to pi times any whole number n, integer n. Okay. And well, I'll just jump to the vertical asymptotes. Our vertical asymptotes are going to be that x equals pi n. And so to show you the range, I guess let's plot these points. So at pi fourths, we would have 1. Pi halves, we would have 0. And 3 pi fourths, we'd have -1. And so again, what would happen is that we would have this function that approaches the asymptotes. But notice that the parent function for cotangent does go down from left to right. Once again, it's going to keep following that pattern. So the pattern for this parent cotangent function is that going from left to right from the asymptote, we using the scale, we go 1, 0, -1. So using this asymptote, using the scale, we have 1, 0, -1. And then we would connect those points with that curve, okay? Now that we've graphed and we see that we are approaching those asymptotes, hopefully you see that our range is once again all real numbers. And notice that our x-intercepts occur every pi units, but this time we had to start at pi halves. So our x-intercepts, we started at pi halves, and then now notice that there's going to be an x-intercept every pi units. So this is very similar to the tangent function as far as how we approach graphing. So again, we'll find the period, which is going to be pi over b. The scale in this case, once again, is pi fourths over b. We found that to be helpful. But notice that this time the vertical asymptotes are different for the cotangent, because cotangent has different places where it was undefined. So for the cotangent, notice that we set our asymptotes equal to 0 and to pi. Okay. Whereas for the tangent function, notice that to find the asymptotes, we set what the function was equal to, what you were taking the tangent of, to -pi over 2 and pi over 2. Notice that if it's the cotangent, we take what we're taking the tangent of and set it equal to 0 in pi. Again, the x-intercept is the midpoint between the asymptotes. We can complete the RST table, but notice that in a cotangent function, if a is positive, we go down from left to right, and when a is less than 0, it goes up from left to right. So that's opposite of the tangent function. So let's take a look and graph example 2. We want to graph f of x equals 1/2 times the cotangent of x over 2. I think you guys realize that this x over 2 is really like 1/2 x. That's right here, all right? So if we want, we could start by finding our period. The period for cotangent, we take pi over b. My b is 1/2. So pi over 1/2 gives us a period of 2 pi. My scale would be pi over 4 over 1/2. So I would multiply by the reciprocal. That gives me 2 pi fourths, which would be the same as pi halves. So that means that my scale here is going to be by pi halves. Oops, 2 pi. I'm like, why isn't that working? All right. And again, you don't have to label everything, but you should make sure that you label it so that you're able to plot your points accurately and that able to follow the pattern. So as far as where the vertical asymptotes go, again, we're going to take what we're taking the cotangent of, which was the x over 2 or the 1/2 x, and we're going to set it equal to 0, and we're going to set it equal to pi. So we see that our asymptotes are going to be at x equals 0 and x equals 2 pi. And notice that this tells us that we can start at 0 and then we'll go every 2 pi units. So our asymptotes are going to be every 2 pi n because there was no transformation there. Okay. So again, there'll be an asymptote at x equals 0. There'll be an asymptote at x equals 2 pi. There'll be an asymptote at x equals 4 pi. Okay. And then going backwards, there'll be an asymptote at x equals -2 pi, x equals -4 pi, etc. We could mark the x-intercepts if we wanted. We can tell that these are going to be every, like in the middle here. So we can see that when we have the x-intercepts that these are going to be every 2 pi units, again, because the period was every 2 pi. So for our x-intercepts, I would start at pi, and then I would add 2 pi n to get the other x-intercepts. So again, there'd be an x-intercept over here at 3 pi, at -3 pi. Notice that all the x-intercepts are 2 pi away. So to get our points, we can plot our parent function. Well, we need to see what's going on first here. So I look and notice that there are no reflections. That as far as the stretches are concerned, that I have this 1/2 as a coefficient. That's going to tell us that that's going to give us a vertical shrink of 1/2. Oops, sorry about that. Vertical shrink of 1/2. And then this 1/2 that's here tells us that there's going to be a horizontal stretch of 2. So the same rules that we've done before. And there are no transformations for this one. They would affect the same way. So the parent function here is going to be cotangent x. And we would use the same points that we did in the parent function example. So we would use pi fourths and 1, pi halves 0, and 3 pi fourths -1. Then all we do is multiply the x's by 2 and cut the y's in half. Multiply the x by 2, cut the y in half, multiply the x by 2, cut the y in half. And so notice that when I make my scale on the y, notice that the point I'm plotting is only going to be 1/2. So I'm going to be dramatic. I know, shocking. And because these points are so low, well, I'll do it that way. All right. So let's say that I made this 1 and I made this -1. Okay. What that would mean if I was plotting the points is I'd have pi halves 1/2, so that would be here. Pi 0, we mark that as an intercept, and 3 pi halves -1/2. And so then we would want to have like a nice curved function here, okay? And so notice that that's your pattern. Try to establish a pattern. So from the asymptote, if you're going from left to right, notice that using the scale, it goes 1/2, 0, -1/2. So I'm at this asymptote. At the scale, I go 1/2, 0, -1/2. And then you can make your piece here, okay? Starting at the asymptote, at the scale, I have 1/2, 0, and then I'd have the -1/2. So I would, probably do some here. Notice if you go from right to left, you go -1, 0. So at this one, -1/2, 0, 1/2. So starting at this asymptote, I would have -1/2, 0 up here. So I can, see that that pattern is going to continue. Okay. And again, I know that these kind of got cut off just because of the graph, but those would really look the same as these did here. Okay. Okay. So the last type of function we're going to look at is I guess two of them, the secant and cosecant function, but these are so similar to the sine and cosine functions as far as we graph them. The graphs of the two remaining trig functions can just be obtained from the graphs of the sine and cosine functions using the reciprocal identities. The y-coordinates, the reciprocal. So notice if you guys look at these graphs, for cosecant, we're going to graph the sine function as like a dotted line as a guide. And then we're just going to use the high point, and that's going to be the minimum of the cosecant function. The low point of the sine function is going to be a high point of that part of the cosecant function. And you can see the same thing will be true for the cosine and the secant. Okay. But because of the idea of the reciprocals, that means that we're going to, again, have these asymptotes. So because cosecant of x is the reciprocal of sine of x, the cosecant function is going to be undefined, and we'll have vertical asymptotes anytime that happens, which is at multiples of pi. So you can see here that we've identified, that the vertical asymptotes occur every pi units. As far as cosine is concerned, those are going to be at multiples of pi over 2, but every pi unit still, all right? But you don't really, it'll be easier once you graph the function, all right? So we have some fun facts about this. Notice that the range of the general cosecant function and the secant function, notice because the range of the sine and cosine functions were -1 to 1. Notice the cosecant and secant functions are everything else, okay? So everything not between -1 and 1. And so again, I think the easiest way to do it is going to be to actually sketch the graphs of the secant functions and cosecant functions, so you see how similar it is to the sine and cosine functions. Because that's how you start. You're going to start by sketching the corresponding sine and cosine function. You'll then draw vertical asymptotes at the x-intercepts. That's the thing, all right? So if you think about the x-intercepts of the sine and cosine function, that means that it was 0, right? So if you take the reciprocal, remember this reciprocal of 0, you can't find, it's undefined. That's how you find your asymptotes. And then you just kind of keep going, and then your peaks become valleys, your valleys become peaks, and you go to town. I think you're going to like it. So we're going to graph f of x equals the opposite of secant times pi x. And so what we'll do here is we want to think about, so I'll think about the guide graph here. We're going to make our table for y equals the opposite of cosine pi x, okay? So you just make your table for the reciprocal function. And you do all your period and your scale and all that by that as well, okay? So let's find the period of this cosine function, all right? So to find the period of the cosine function, remember that's 2 pi over b. So 2 pi over pi gives me a period of 2. Now the scale. The scale is pi over 2 over b. So pi over 2 over pi ends up being 1/2. So that tells me that the scale of my graph is going to be by 1/2. Oh, oops. Sorry. Okay, so the scale of my graph is going to be by 1/2. As far as let's just plot the function before we look at where the vertical asymptotes are in this case. Okay, so if we want to graph cosine of pi of x, notice that this negative right here tells me that there's a reflection in the x-axis, which means that my y becomes negative. And this coefficient here, this b value, tells me that there's going to be a shrink of 1 over pi for x. And then y, there was no, like the amplitude was just 1, so we're good there. And this graph doesn't have any sort of translation. Now the issue with cosine of x is that we do have those 5 points. So 0, 1, remember cosine and sine, we use intervals of pi over 2 for the critical points. Pi over 2, 0, pi negative 1, 3 pi over 2, 0, and then 2 pi 1. And then we'll just make the adjustments in the table just like you did normally. So we're going to take the take the opposite of all the y values. And then we're going to multiply all the x values by 1 over pi. So basically you're going to divide the pi out. You could think about it that way. So dividing by pi, we end up with 0, negative 1, 1/2, 0, 1, 1, 3 over 2, 0, and then 2, negative 1. Okay. And so I just want to plot those points. Okay, I'm going to plot those points. Oh, let me do the scale, sorry. On the y, we'll go here. We'll make each little grid by 1/2. Okay, and so let's plot 0, negative 1, 1/2, 0, 1, 1, 3/2, 0, negative 2, negative 1, or 2, negative 1, sorry. Okay. Now you guys, this pattern then is going to repeat, right? So basically we go up, we go down. So if we continued, we'd go up, we'd go down, right? So then going in this direction, notice we go up, we go down, we go up, we go down, we go up, and then we go down. We're just going to plot those points. And if we were actually, and you don't have to draw this, I wouldn't, what happens is that this is what the cosine graph would look like, okay? But now what you're going to do, and this is the important piece here, is that you're going to draw vertical asymptotes at all x-intercepts. So at every x-intercept, you are going to draw an asymptote. So every time you see an x-intercept, you're going to draw an asymptote because you can't take the reciprocal of 0. So those are my asymptotes. And now to get the actual graph, any low point becomes a high point, and so you basically just approach the asymptotes. This high point is a low point, you approach the asymptotes. So some people are like, oh, it looks like a lot of little parabolas. Yes, but these aren't technically parabolas, okay? And then on this side, we would go here. This side, we would go here. So we just start at those maxes and mins of the cosine function, and then we just go towards the asymptotes, and that's it. And you might say, oh, well, the asymptotes are notice that they're every 1 unit, okay? They are, but notice that a whole cycle, like one goes up, one goes down, one goes up, one goes down. That is important to notice. That makes the full period, okay? If we have the vertical asymptotes, notice that if we're looking at the vertical asymptotes here, that we didn't start at 0, we started at 1/2, but that we went every 1 unit. And so our vertical asymptotes would be at x equals 1/2, and then we go every n units. You could also put n plus 1/2, that's fine as well, okay? If we've done that graph, then it should be pretty quick for us to do this last graph. This last graph, we're going to do f of x equals 1/4 times the cosecant of x plus pi/4. And again, what we'll do is we're going to make our table and just fill out all the other information, well, fill out the period and the scale for y equals 1/4 of the sine times x plus pi/4. Now, just like normal, if necessary, we would need to factor it out and turn it into that like b times the quantity x minus c form. Okay, but I don't think but we don't need to do that in this case. All right, so let's start by finding the period. That seems to be a good thing for us to start with. So our period is going to be, again, for sine 2 pi over b. And notice that b is just 1, because we don't see anything. So our period is 2 pi. Then our scale is going to be pi over 2 over b, which is just pi over 2. So that will be our scale, is just going to be pi over 2. And again, I just like to label a lot of the things on the axis just so I can kind of tell where everything is. That's just me. And then let's just see what is going to happen to our function. Notice that here our y value was affected by 1/4. So there's not a reflection, but there is going to be a vertical shrink by 1/4. Notice that the b value is 1, so there's no horizontal stretch or shrink. Notice there's no reflection, but notice that this will give us a translation. This tells us that we're going to go left pi/4, but we'll leave y the same. So our parent function here, again, is going to be the sine of x. And again, for sine of x, we do need the 5 values. So we have 0, 0, pi halves 1, pi 0, 3 pi halves negative 1, and 2 pi 0. So I'm going to just multiply all the y values by 1/4. Oops. And leave the x values the same here. I really need to make my tables bigger. And then we're going to subtract pi/4 from the x values. So x minus pi/4 is negative pi/4, 0. Pi halves minus pi/4 is pi/4, oops, pi/4, 1/4. Pi minus pi/4 is 3 pi/4, 0. 3 pi halves, which is like 6 pi/4 minus pi/4 is 5 pi/4. And then 2 pi minus pi fourths would be 7 pi fourths. Okay. And so if we start plotting those specific points, notice that my scale was by pi halves, but that means that these little ones between would be where the pi fourths are. So how handy was it that we were able to do that? And notice that we're going to be going to 1/4 and negative 1/4. Well, you guys, I'm going to enlarge this scale. So I'm going to do, this is a half. No, I'm going to do that this is a half up here. And that this is 1/4. And this is negative 1/4. And this is negative 1/2. Just so it's not crammed, okay? So that's the fun thing about adjusting your scale. And so then we could plot those points now that I have a scale everywhere. So my negative pi fourths 0 would end up being right here. Okay, so it's not on a heavy tick mark, but it was on one that I was able to graph. And then pi fourths would be at 1/4. 3 pi fourths would be at 0. 5 pi fourths would be at negative 1/4. And 7 pi fourths would be back at 0, okay? So notice in this one, we're not on the heavy tick marks, but we're right between them every time, okay? So what would happen is that we would just keep following this pattern. So I'm on my way up here, so the next half tick mark, I would be up, next half tick mark down at 0, and then the next one I would be down here. And then again, just keep following that pattern. And notice that this one is just a little bit different because you're doing every half of a tick mark, or not every half of a tick mark, but you're going between the tick marks instead. But still, it should be like a nice zigzag pattern. There shouldn't be any double zigs in there. And I would draw the vertical asymptotes every time that you see those x-intercepts again. Okay, drawing those asymptotes in. Mine are not very pretty, sorry, okay? And then once you draw the x-intercepts in, again, what would have been like your maximum, you're going to make that the minimum of that little piece of our cosecant graph. So notice I don't even need to connect the points for the guide function. So in this case, I don't even need to connect the points for the, I don't even need to connect the points for the sine function. I'm just going to use those points as guides. Oh, and if I wanted my vertical asymptotes, I noticed that they occur every pi units. Yep, okay. So notice that I have one at, so they occur every pi units. Notice that it's always half a period. You guys notice that the asymptotes for the sine and cosine, so sorry, for the cosecant and secant occur every half period, okay? So every pi units in this case. And I always like to start with the positive one. So my first asymptote was at 3 pi fourths. And then I see that they're going to occur every pi units. Okay? And that's what I need you guys to know about those trig functions. And we will discuss damp trig functions at another time, okay? So hopefully you guys got this, and you've got, if you need to rewind, if you need to contact me, just let me know, and good luck on the homework.